Pn of x, so again there are infinitely many variables, just denote the sums of the nth powers of the variables, the sum of all the nth powers, xi power n. Okay, another way of saying it is that this is nothing but the monomial symmetric function corresponding to the single part n alone. Okay, so that's the power sum symmetric function. P0 we don't define, or we can define it to be 0. Okay, so P1 onwards, the definition is what we have there. And as we did with the E's and the H's, if you are given a partition lambda 1, lambda 2, lambda L, we define the power sum P sub lambda to just be the product of the P lambda 1, P lambda 2 and so on. Okay, now let's try and, having defined a new set of symmetric functions, what we're going to do is to try and express this in terms of the previous ones, which is the M's, the H's and the E's. Now to do that, let's start by deriving the generating function, just as we did for the E's and the H's. For the power sum symmetric function. So as we did for E and H, let's write the following. This is for n going from 1 to infinity, because as we said, p equal to 0 is just defined to be, for 0, p0 is 1. Okay, so this is the generating function, pn t power n. Now, let's see what this is. This is just the summation over all n, summation over all xi over I, xi power n times t power n. So I'm just going to put the t power n inside and think of it like this, summation xi power n t power n. And therefore, what is this sum? I will sum over n first. Sorry, I'll sum over I first and put the sum over n inside. If I do that, I just get t power n times, so let's write this out. So what is this? This is txi. Sum over n, I'm just summing txi the whole power n, and that's just txi divided by 1 minus txi. Okay, now let's do the following to this. This is a lot like 1 over 1 minus txi, except that's a txi on the top, right? So let's think of it as follows. You just take the following power series, look at log of 1 minus txi. Okay, think of it as a power series in t. So the logarithm is some power series. And now when you take the derivative of log, so it works like in ordinary calculus. So what's the derivative of log? Let's write that out. So if I have a power series, so I'm going to try and take derivative with respect to the variable t of log of something, in this case log of 1 minus txi, this just becomes 1 over 1 minus txi. That's the usual derivative. But then I have also a minus txi to take derivative of, and sort of by the chain rule, which applies exactly the same way, I get a minus xi on top. Okay, so that's what the derivative looks like. Now what do I have here? I need to get 1 over 1 minus txi on the denominator. That's all right. And I need txi on the numerator, right? So how can I get a txi on the numerator? Well, I just take the derivative of this. Okay, and then multiply the answer by a minus t. So what I need to do really is to take minus t ddt of log of 1 minus xi. Okay, and then I need to sum that over i's, I going from 1 to infinity. Okay, so let's do that. So what's this? So I can pull the minus t ddt outside. So I'll think of it like this, minus t ddt of log of the summation. So I can also absorb the minus. So let's do this, log of the product 1 minus dxi. So that will be, log of the product is sum of the logs, and I'm also going to absorb the minus sign here by just putting that as the exponent. Okay, so all the usual properties, algebraic properties of log I have used. Those all work the same way when you have power series in play. Okay, so that's the final conclusion after sort of rewriting it in this form. And of course, the reason for wanting to rewrite it like this is because this guy here is something we recognize, right? So this, if you remember, is exactly the power series of h, right? The product of 1 over 1 minus dxi, that was exactly the power series generating function h of t. So what have we proved? We have proved that there is a relationship between the generating functions of p and h. P is obtained by taking d times the derivative, t ddt of log of ht. Okay, and again, what's that? That's again by using the chain rule. That's just t h prime t by ht, where h prime just means take the derivative with respect to t. Okay, so that's the equation in some sense, and I'm going to rewrite that equation in a form which allows me to calculate the p's in terms of the h's. So I will rewrite this equation as pt ht is t times h prime t. Okay, so what are we going to do now? You think of that as your equation, connecting power series in t on the left side and the right side, and compare coefficient of every power of t. So compare coefficients of t power n for all n. Okay, so in fact you'll only have coefficients from t power 1 onwards, as you can see on both sides. And when you do this, here's what you get. Okay, so on the left side, this coefficient is nothing but PR of x, h n minus r of x. Okay, that's what you get when you multiply two things out. That's the coefficient of t power n. Now on the right hand side, it is, well, I have to do t times h prime of t, and when I do that, what will I get? Well, I just get n times hn. Okay, and you get this because, so of course this is all true for n greater than equal to 1, n hn, because you're taking the derivative of the power series h, and so summation hn t power n, the derivative will give you n t n minus 1 times nhn. Okay, so I've just taken the derivative. So okay, great. So that's the final equation we were after. This allows us to do the following. This allows you to recursively compute the p's in terms of the h's. Okay. Now, we have done this sort of thing once before when we tried to connect up the h's with the e's. So in this case, I'm just going to write out these equations one by one. If n equals 1, it says p1 equals h1. And n equals 2, it says p2 plus p1 h1 equals 2h2, and so on. Okay. So the next one will look like p3 plus p2 h1 plus p1 h2 plus h3, right? And this should equal 3 times h3. Okay, now I'm missing an h3 on that side, sorry. So there's no h3. That last term is what becomes a 3h3 on the other side. Okay, so and so on. So I can keep going like this. Now the point is, we can recursively compute the p's in terms of the h's from this equation. Okay, but before we do this, let's also get the e's in play. Okay, so I will come back to these equations, but before we do any further computation, let's also figure out what the corresponding situation for e becomes. So I can also get an equation which relates p's with, so recall that pt is t ddt of log of ht. But if you remember how h and e were related, h e minus t was a 1. Okay, so I can rewrite the equation on top in terms of t dt log of e minus t with, it's the inverse of that, right? So h of t is 1 by e minus t. So this is log of 1 by e of minus t. Okay, so I can pull that out. Write it as minus t dt log of e of minus t. Okay, so there are many minuses to be kept track of here, but let's do this nevertheless. So this is minus t log of et, derivative will give me log of e minus t, 1 by e minus t, e prime minus t into a minus 1. So that cancels this and gives me a plus. So that's my final answer. P of t turns out to be t e prime minus t by e minus t, or an alternative way of writing this with fewer minuses is to replace all t's by minus t. So I get p minus t on the left side and e prime t divided by et. Okay, so you can think of this as again an equation that relates p minus t, the power series p minus t with the power series et. Okay, and once more what you can do is the same thing that we did before, which is you bring the e minus t from down here back to this side as e of t. So same sort of equation that we had with h, except you've got some additional minuses. Okay, so once more we rewrite what this gives rise to. It says, so the coefficients of p minus t, well, they are not PRs, but rather minus 1 power r PR. Okay, so now I have minus 1 power r PR of x into E n minus r of x. And on the right hand side, I have to figure out what I get. And sort of by similar arguments, I have minus n E n. Okay, so this minus I push to the other side and call this minus 1 to the r minus 1. So here's an equation which tells me how the PRs and the E's are related. Okay, and just like in the case of H's, this can again be rewritten in terms of the actual P1 becomes E1, P2 becomes well, it satisfies the equation minus P2 plus P1 E1 equals to E2 and so on. Okay, now what we can do is to solve for P's now in terms of E's recursively. Okay, so what you'll get is the following. So now from the first equation I already know P1 is the same as E1. And second equation P2 turns out to be E1 square minus 2E2, etc. Okay, so I can compute the P's in terms of E. So let's just say what the next one looks like. It's E1 cubed minus 3 E1 E2 plus 3E3. Okay, now not just this, you can, like we did earlier with the E's and the H's, you can also invert the relationship. In other words, given these equations, so given this equation star, I can use it to write the E's in terms of the P's also recursively. Okay, so let's do that. So let's, from this equation, we'll write it as E1 is actually P1. Okay, now let's look at the next equation where something interesting starts to happen. E2, when you write it in terms of P2, gives us the following. It says E2 equals let's see, it's E1 square, which is actually P1 square minus P2, but then I have to divide by a 2. Okay, that's because the E2 came with a coefficient of a 2. Okay, now when I start to do this, you'll see that E3 again, recursively. So when I write this, E3 similarly will become what? P3 minus E1 cubed was P1 cubed, plus 3 E1 is P1, E2 is what we just wrote out, P1 square minus P2 by 2. So I do all this, but then at the very end, I have to divide by the 3. Okay, because that's the coefficient in front of the E3. So what this says is that I can write the ENs in terms of the PNs, alright. Okay, and recall that just like in the earlier case, that establishes that the P's also form a basis. Okay, but so the important thing here is that you're going to end up with not all integer coefficients, but you're going to get rational coefficients. Okay, so this guy is actually a power sum symmetric function because it's corresponding to the partition 1 1. This is corresponding to the partition 2 divided by 2. This next guy I can think of as P3 is just a power sum symmetric function P corresponding to 3. P1 cubed is P corresponding to the partition 1 1 1 plus we will get two terms 3 by 2 P1 cubed, which is again P of 1 1 1 minus 3 by 2 P1 P2. So that's minus 3 by 2 P corresponding to the partition 2 1. Right. So I've just rewritten these very same terms on the numerator in terms of partition. So this is like a linear combination of the P lambdas. Okay. So observe that. So this is a repetition of the arguments that we gave when we wrote H in terms of E's or E in terms of H's. Therefore, the conclusion is the following. Given lambda a partition of D, E lambda can be written as a linear combination, of the P lambdas, maybe I should call it P mu partition of D, but the coefficients that I'm going to need are not integers anymore, but rational numbers. So it belongs to the rational span of the P mu's. Okay, so the corollary is that the P's also form a basis. Of what is the question. So if you say lambda D, then this is all symmetric polynomials, homogeneous of degree D, but we remember we said this is over some ring K, and we've often been looking at K to be the integers, but this is only if you take that K to be the rational numbers. So it forms a basis over the rational numbers. Okay, so just something to keep in mind that you'll start needing rational numbers as soon as you pass to the power sum symmetric functions. Now the interesting fact again that we've looked at before. So when you write the E's in terms of the H's or the H's in terms of the E's, what do these equations look like? Right. So remember when we did that for the H and the E, the equations which told you how to write H in terms of E actually looked exactly like the equations which told you how to write E in terms of H. Now, something similar happens in this case. So if you recall, let's just write the equations out maybe. So for P and E, the equations are like this. P1 equals E1, P2 equals E1 square minus 2E2. Plus 3E3. Now on the other side, let's do it with respect to the H's. So P1, so I'm just using the first equation we wrote out. P1 turns out to be H1. P2 turns out to be minus P1 square. So that's minus H1 square. Plus 2H2. Okay. P3 turns out to be the same thing with H. So H1 cube minus 3 H3. P4 will be the same as what you have in terms of E's, but with one minus sign. Okay. Now, etc. So I'm not writing all of them out. Now, if you sort of go back and see what the general equation look like, they both differ by a minus sign. So let's just scroll up and look at what those equations look like. Okay. So here's the equation in terms of n for a general n. it looks like this. PR Hn minus R, okay, is NHn minus n. So if on this side I have H and NH on this side, okay. And when I do that, I have PR here. Let's skip to the case of E's and look at what that becomes. In the case of the E's, the equation is again En minus R in place of Hn minus R, Nen in place of Nhn, but what I have here is minus 1 to the R minus 1 PR. Okay, so there is the only difference between that earlier equation and this one is that PR is replaced by minus 1 to the R minus 1 PR. Okay, so that's really the only change, and that's exactly what happens when you sort of look at these two equations side by side. That's what's going on. Okay, so let me just summarize this as the following fact, or a lemma or a proposition if you wish. So recall the involution that we talked about, the involution omega from the ring of symmetric functions to itself. So what it does was it maps ER to HR or E lambda to H lambda if you wish, right, and vice versa. Now if you take this involution, so recall this involution, then when it acts on PR, it just maps it to minus 1 to the R minus 1 PR. Okay, and so I won't actually do the proof in full. The proof is just what we have said already, that when you write out these two equations in terms of H and E, you see that they correspond exactly, except for this minus 1 to the R minus 1 factor in fact. Okay, so take one of these equations, apply omega to it, apply the involution, and then you will, you will more or less get the other equation. Okay, good. So this is the action of the involution. Now the point is, if you take, this is for a PR, but what about for a general P lambda? Okay, so remember P lambda is just a product of P's. And omega was a ring homomorphism. So it's just omega of P lambda 1 multiplied by omega of P lambda 2, etc. And each omega just gives me a sign. Okay, so if you sort of look at what this finally gives me, this gives me minus 1 power lambda 1 minus 1, lambda 2 minus 1, and so on. Right? So this is lambda 1 minus 1 plus lambda 2 minus 1 plus etc. times the original P lambda itself. Okay, so there is some sign in front, and the precise formula for the sign is exactly the following. So we say that omega acting on P lambda gives me a sign epsilon lambda, where epsilon lambda is, well, what's this? It's minus 1 power the sum of all the parts of lambda, right? And that's what we call minus lambda, mod lambda, and minus, there are many ones, right? How many ones do you have? As many as there are parts of lambda. Okay, so this is called the length of lambda, the number of parts in lambda. Okay, so mod lambda just means summation lambda I 1 to L, and length of lambda is just that number L, which tells me how many parts, non-zero parts my partition has. So this total sign in front is just this number, minus 1 power mod lambda minus length lambda. Okay, but the beautiful thing here is that the omega acts in a very, very simple manner on the power sum symmetric functions. See, on the E's and the H's, it sort of did some kind of funny interchange, right? E's went to H's and H's went to E's and so on. But in this case, what it does is to just, well, either multiply it by a plus 1 or a minus 1. So that's a nice thing about omega. So what does it mean? It says that omega, the P lambdas are nothing but they're eigenvectors for the action. So P lambda, lambda are actually eigenvectors for the action of omega. Okay, and of course the eigenvalues are plus 1 or minus 1. So with eigenvalue being lambda, epsilon lambda. So with eigenvalues being the epsilon lambdas, which are all plus or minus 1. Okay, good. Now, so we have worked out the action of omega on the P lambdas. Now we figured out how to write p's in terms of h's or h in terms of p's, but that description that we gave was sort of recursive, in the sense we could only do it step by step. Assuming we knew everything until that point, we could then compute the next one. So here's a non-recursive way of writing the p's or h's, the h's in terms of the p's, for example. Okay, so this is a non-recursive description of how to write h in terms of p or how to write e in terms of p. Okay, so this is specifically for the hns and the ens. So let's work this out. So recall again, it's a generating function calculation. How do we get pt? It is just t ddt of log ht. Right? Now, what does this mean? This was by definition summation pn t power n going from 1 to infinity. And so what I can do is divide both sides by this t, okay, and then I integrate. So instead of the derivative, I just apply the integral to both sides. So when I do that, what I obtain is log ht is summation pn t power n minus 1 n going from 1 to infinity, and I'm looking for the integral dt of this, okay, term by term integration. And the constant term is a 0, okay, because when I compute log of a power series, I always get the constant term 0 on the left side. Okay, so that sort of fixes the constant terms. So let's do the right side. This is just summation pn t power n by n. Okay, n goes from 1 to infinity. So that's what log ht is, and so now I just have to exponentiate both sides. So again, we're just performing various power series operations on formal generating functions. So here ht is just obtained by exponentiating the right hand side. The right hand side looks like summation pn. Okay, and so it's a product of the separate exponentials. Okay, now product n goes from 1 to infinity of this. So what this becomes, so if you recall what the exponential is, it's a series now. So this for, let's say, each term looks like summation pn t power n by n raised to some power, right? So now that depends on n in this case. So let's say this is some alpha n by alpha n factorial. Okay, alpha n goes from 0 to infinity. So I'm just giving the various terms, the various summation indices, different names. That's all. Okay, good. So now when you sort of look and find out what the final thing is, right? What's the left hand side is summation h d t power d, let's say, d equal to 0 to infinity. Okay, now you compare both sides of this equation and ask, well, can I use this to find a formula for hd? Okay, and well, of course, yes, because all you have to do is figure out what the coefficient of t power d on the right hand side is, and here's what it becomes. Okay, so if you sort of see what you're doing here, you're taking this n, right? So there is one term for each value of n. So think of those as the various possible parts. Okay, n can be 1, 2, 3 different parts of a partition, and alpha n is sort of like the multiplicity of a part. Okay, so if I take this particular term t to the n alpha n, it's as if I'm taking the part n alpha n times. Okay, so I suppose I pick out that particular term t power n alpha n from the nth bracket. Okay, so like that, from each bracket for each n, I'm going to pick out some alpha n, right? So what is this going to be a sum over? Well, over all possible tuples alpha n's going from 0 to infinity, such that summation n alpha n gives me the d that I have fixed, right? So I should sum over all such possibilities. Now, once I do that, what's the term, what's the coefficient that I get? So there are sort of two such numbers on the bottom. So there is, so firstly, for each n, I've got n power alpha n factorial, n power alpha n factorial. Okay, and so product over all such terms. This is a product all n's. Okay, and the numerator is, well, it's going to be p, pn occurring alpha n times. So this is just pn to the alpha n, again product over n. Okay, and finally the coefficient of t is just d. Okay, so if you sort of see what we have done here, this is really the following. The numerator is just, so I'm going to think of this, alpha, the choice of alpha n, such that this property is true, that summation alpha n alpha n is d, as being nothing but a choice of a partition. So this is as if I have chosen the partition lambda, which is n occurring, alpha n times. Okay, so that's my choice of partition. So if I think of it in those terms, I can just rewrite this as follows: p lambda divided by this number which one calls z lambda. Okay, and what is this number z lambda here? It is just this, the parts are, so if you think of, so sometimes we write this in what's called multiplicative notation. 1 occurs alpha 1 times, 2 occurs alpha 2 times, 3 occurs alpha 3 times, and so on. Then the z lambda is just a number, product of alpha n factorial and product n power alpha n. Okay. Okay, there. So lambda is just the following number. It is n power alpha n. So it's just 1 into. So this is multiplicative notation for a partition. It says 1 occurs alpha 1 times. But now what I am writing is the actual number: 1 power alpha 1, 2 power alpha 2, 3 power alpha 3. This is now an integer here. And then I have to divide by the factorials, right? By alpha n factorial. So that's alpha 1 factorial, alpha 2 factorial, etc. So this is the number z lambda corresponding to the partition lambda, which is written in multiplicative notation. So okay, so this number also turns out to be the centralizer in the symmetric group, the cardinality of the centralizer of an element of whose cycle type is given by lambda. Okay, anyway, so what we have managed to do is to say what the equations are which allow you to write h in terms of p. Okay, and this is a very important and useful equation which tells you how to write h d in terms of p lambda. And if you apply omega to both sides of this equation, you will get a way of writing ed in terms of the p lambdas. So you're just going to get some signs on the right side. Okay, good. So that's the equations for h and e in terms of h, in terms of p. And so one can also do something concerning the monomial symmetric functions. So this is the monomial expansion of p, the Schur function of the power sum symmetric function p lambda. And so let me just quickly sketch what I'm looking for. So a given p lambda is nothing but p lambda 1, p lambda 2, p lambda 3, and so on. And p lambda 1 is like summation the lambda 1th powers of the variables. It's some more I xi power lambda 2, and so on. So that's what this product becomes. So each term itself is very simple, just the lambda 1th powers, lambda 2th powers, and so on. Now, when I multiply these out, the question when I'm asking what's the monomial expansion of this p lambda, what we are asking is what monomials can possibly arise, right? When you actually do this expansion, and it's sort of very easy to see what monomials you can get. Well, what can you do? For example, from the first term, you can take an x1 power some lambda 1. From the second term, I can take, let's say, suppose I do this x2 power lambda 2. From the third term, I should take something power lambda 3. Fourth term, something power lambda 4, etc. Right? This is what a typical thing looks like. Now, the thing is, from, say, the third term, I don't need to have chosen a different variable. I can choose the same variable again, x2 power lambda 3. Or from the fourth guy, I can just choose my x1 power lambda 4 again, and so on. So what this means is that I'm sort of allowed to do the following. When I try and construct a monomial, I will just imagine that I have boxes which I'm allowed to fill. So it's anything power lambda 1, anything power lambda 2, and so on. And the variables I choose here can be any one of the xi's. Okay. So I can sort of choose some of them same, some of them different, and so on. So x3 lambda 1, x3 lambda 2, x2 lambda 3, x1 lambda 4, etc., etc. Now, depending on what I put here, I will get the total power will become different. So, for example, the one that I just wrote out, x3 is in the first two boxes. This is like x3 power lambda 1 plus lambda 2, right? Lambda 1 and 2 has sort of gotten together. Then lambda x2 power lambda 3, etc. So what this argument proves, as you can convince yourself, is the following. What monomials can you possibly get when you expand p lambda? Okay, this will become a sum of, well, some m mu's. Now my question is, what mu's do I run over? Which mu's will come when I do this expansion? Okay, and the answer is the following. You just write out these partitions. So imagine writing out these numbers, lambda 1, lambda 2, lambda 3, and so on, lambda L. Okay, so I write these L non-zero parts, and then what I do is I'm allowed to club any number of them together. Okay, so for example, I can choose to club lambda 1 with lambda L, lambda 2 can be itself, lambda 3 and 4 can be in one group, and so on. Okay, maybe all the rest are in another group. Then what I do is I just add up the numbers in each group. So lambda 1 plus lambda L will become one thing. Lambda 2 is another number. Lambda 3 plus 4 is another. And all these guys together, they add up to something else. And the monomial that I'm going to get mu will be the type, it's of that form. The parts of mu are all sums of some parts of lambda. Okay, so I'm not giving you a very precise sort of definition here, but the basic idea is that this partition mu, the parts of mu are obtained by doing the following process. You write out the parts of lambda and you first split them into some disjoint classes and you just add up the numbers in each class. Okay, so the numbers in each class are going to be the mu's. You arrange those numbers that you get in descending order, and that is going to be your partition mu. Okay, and now you do this this sort of partitioning. This array, whatever, writing the lambdas into classes in all possible ways, and every way of doing it gives rise to one single mu. Okay, and it may therefore give rise to the same mu many times also, if the numbers map in that manner. So in that case, you will get the same mu occurring many times. So you will get a larger coefficient as well. Okay, and the coefficients just come. The correct way to write it is what I have already done. Okay, anyway, so I'm just going to leave this as as an exercise for you to formulate in more precise terms and prove this.